Hello everyone, let us start lecture 18 and the course is phase diagrams in single component and binary systems. And today's topic will be on the same aspect what we have been talking for the last few lectures, which is phase equilibria in single component, which is H2O system, and we will try to complete the phase diagram considering the vapor phase transformation. In fact, we have already done the phase diagram for solid to liquid transformation. We will continue, we will extend this when we try to see liquid going to vapor, which is evaporation, and solid going to vapor, which is sublimation. Fine. So, these two processes we will also consider. So, that means if we see that, we will try to complete the phase diagram considering phase equilibrium and single component. And till now what we have done? We have looked at the pressure temperature plot. This is 0 degree Celsius, this is 1 atmosphere, and this point, on this point we have drawn dP dt, which is equal to negative. That is what we have seen. Now, we will continue our thing on, this is for solid liquid equilibrium. Now, we will try to do it for liquid vapor and solid vapor in case of water system. Now, interestingly, these two phases can be taken as condensed phase. Okay. If they are condensed phase, so we will see what happens if the vapor forms. But let us say I want to see here what we have done. How did we perform this particular analysis? We have performed this by G versus T plot, pressure kept constant. Let us say 1 atmosphere, we have seen that this is G S and this is G L and this is my 0 degree Celsius, and at this point delta G equal to 0. Okay. So, that is what we have done. Now, let us see what happens if we keep temperature as constant and try to see G as a function of pressure change. Now, let me start with delta G equal to V dP minus S dt. I can write delta G dou G. So, let me just write this equal to V. So, for solid this constant temperature, for liquid it is this. Now, if I try to see similar kind of plot for solid to liquid transformation, then I can get a plot like this. Let me just draw that. G as a function of P. Let us say I am keeping temperature as 0 degree Celsius, and Vs is a positive quantity, molar volume. This is also positive, but interestingly Vs for H2O is greater than VL of H2O. So, when I try to see G versus P plot for solid and liquid, both would be having positive slope. So, now let me draw a solid plot. This is, let us say, G S, and slope is nothing but V S. Now, let me draw liquid. So, that liquid slope should be less than the solid slope. So, the liquid line would be like this. This is G L, and here the slope is V L. which is the molar volume of liquid, and that other one is molar volume of solid. And let us consider that this is for 1 mole transformation, and we will see that this point is nothing but 1 atmosphere if we keep this temperature to be 0 degree. In fact, any point, let us say I fix this temperature is fixed. So, at this point I should experience the different pressure, which is let us say P prime. So, that pressure we should experience. Let us say temperature is changed to T prime, this is T prime, and that time this point should have been P prime. Okay. Like that way the transformation takes place. So, in fact, both the data can actually corroborate each other. Okay. So, that is what we get that, and in fact, there also this slope will have to be considered, and then you will see it will actually have a negative slope. Because of what? Because of the molar volume difference for solid to liquid transformation, if we consider, that becomes negative. So, that is where dP dt becomes negative slope. So, again you will get that negative plot. So, now coming back to a situation of condensed phase to vapor phase, either evaporation or sublimation. Okay. Now, when we do that, I can write this equation, a generic equation del V, where del H is basically transformation enthalpy change, del V is the molar volume change during transformation. Here transformation is basically phase transformation, please understand that, and T is basically the transformation temperature. Okay. Now, del V, let us say I am considering C to condensed phase, which is considered as C to vapor phase V. C to V, then I have write vapor con, I can put it as CON to VAP. Okay. So, then del V equal to V vapor minus V condensed. Now, if I try to find out the difference of molar volume when a condensed phase transforms to vapor phase, that difference become extremely high. In fact, vapor is very high compared to in case of water. Okay. Not only water, even CO2 case also, this will be very high. Now, since we will be considering CO2 also while considering phase diagram in single component. Now, once we write this, we can make it like V vapor. I simply write V. So, this equation would become V. Interestingly, let me just consider this vapor phase is ideal gas. Let us assume that, this is assumption. Let us consider that. So, if it is that and we have considered 1 mole, so then P V equal to R T. So, it becomes V would become R T by P. So, then this equation would become can write this. I have taken it out considering that delta H is not a function of temperature. So, it is a constant term and R is constant. So, that is what I have taken it out. So, if I do integration, then I will get ln P equal to delta H by R minus 1 by T plus constant. I should get this. Okay. So, now interestingly these equation or I would say this particular equation can be termed as Clausius-Clapeyron equation. Fine. So, we get this. Now, let us say, and this actually if I try to plot this for solid to liquid, then definitely I would get a plot which reflects the equilibrium between a condensed phase and the vapor phase. Condensed phase could be either liquid or solid, and I should get that two plots. Interestingly, if I try to look at analyze what is P, P is nothing but saturated vapor pressure, and this is a function of T. And that function if you see it is basically related exponentially. So, if T increases, pressure, saturation vapor pressure would also increase. So, now this saturation vapor pressure of condensed phase, it means the vapor molecule of the condensed phase, that molecule how much pressure it exerts on the wall of that particular closed system. Okay. So, that is basically saturation vapor pressure, and if you fix a temperature and if you keep a closed system, definitely saturation vapor pressure or the saturated vapor pressure should be achieved, which is nothing but the equilibrium condition. Okay. Now, we have taken an assumption that this is a fixed of constant quantity, but this can actually vary with temperature, can be dependent on temperature. So, that case we can actually use Kirchhoff's equation. So, where I can write delta H T any other temperature for water, I can start with 298 plus del Cp, which is the difference between, in fact this is del Cp, this is the reference and this is del Cp for condensed phase and the vapor phase Cp difference, T minus 298. We are starting from 298, which is the reference value. Okay. Now, I can use this formula. Let me put it here. If I put it here, then I should get okay. So, this should be the, so if I put it here, it should be the thing. So, then I can, and here it will be P. So, I can write it like d ln P would be equal to fine. So, then I can d ln p would be equal to this would go into. So, in fact, delta H 298 minus 298 into delta C p is basically a constant. Let me put it as A. So, A divided by R T square, and remember delta H 298 is basically a reference value of enthalpy. Okay. So, this reference value should be a constant, and this del Cp is also constant. I am taking that assumption that del Cp does not change with the temperature, but it is not a 0 value. Okay. So, this is a constant dt. Again, this is a constant, R is a constant. I can put it as B T dt. So, delta Cp R equal to B. So, then I can write ln P equal to A. In fact, R, I think I can take R in that particular constant. So, I can write minus A by T plus B ln T plus constant. Another equation we are getting. Okay. So, this equation can be used to find out plots on PT space, PT plane, and this should be between solid vapor as well as liquid vapor, these two transformation. Now, one can actually take those values, those free energy, enthalpy values and delta Cp values, and calculate A and B. All those things can be done if during the sessions when we discuss questions and their answers, we can take one examples. In fact, so these equation for water system can be plotted. So, we can plot ln P as this particular value, which is Kelvin minus 1, inverse of Kelvin scale, and this is let us say 100 degrees Celsius for water, and let us say this is I am talking about liquid to vapor. Liquid to vapor, let us say 1 atmosphere if I consider, then my boiling point would be 100 degrees Celsius. So, if I take this is as 100 degree and 1 atmosphere, so this value would be 0 because ln P would be 0, and from there if I start, this plot would go like this. Okay. This ln P would change this way as we change the temperature. Okay. So, that is the way we get that plot. In fact, when I take this equation and try to draw the equilibrium between liquid and vapor and the solid and vapor, I can actually get 3 equations. In order to complete, I can get three equations which will decide solid liquid equilibrium, and then another one is solid vapor. So, one equation would be P would be equal to del H del V ln T plus constant. How come it gets del T del P del T equal to del H del V T. So, from here I can get P equal to dP equal to del H del V dt T. This is a constant term, fine. So, then I can get dP equal to del H del V ln T plus constant. So, that is what this equation talks about solid liquid. So, then for liquid vapor it would be ln P equal to minus A, let us say for liquid, or I would say A prime for liquid by T plus B prime ln T plus constant, and in this case it is ln P equal to minus A double prime T plus B double prime ln T plus constant. Okay. So, this three equation I can plot, and the plot would be like this: T pressure. First plot is, which is equation 1, 2 and 3. So, first plot is this. This is equation 1, and the second one is this, and the third one, this is second, and the third one would be like this. This is third. So, this particular green line is solid vapor, this one is liquid vapor, and here it is solid liquid. Okay. So, now you see all the lines will be crossing one single point, crossing through a single point, and that is nothing but triple point. We will talk about this triple point later. Now, you see that all those lines are extending into the single phase zone also. So, here it is solid, here it is liquid, and here it is vapor. So, if I do not extend that lines through the to the single phase zone, only remain in the two phase zone. So, then I will get a plot like this. So, where this is vapor, this is solid, and this is liquid, and all the lines are actually indicating equilibrium between two phases, and at only one point, which is the triple point, where all three phases can coexist under equilibrium. So, this is nothing but phase diagram in water system. And in order to do that, we have taken these three equations, and this A prime B prime should be calculated for liquid vapor transformation enthalpy change as well as del Cp change. A double prime and B double prime should be calculated on the basis of enthalpy change for solid to vapor and Cp change for solid to vapor, and that gives us two curves. This is for liquid solid, liquid vapor, this is for solid vapor, and this one is for solid liquid. Okay. So, let me stop here. We will continue our discussion on this. Now, at least we could see that we have a kind of phase diagram which demarcates three phases with the help of three boundaries, and those boundaries are actually equilibrium point boundaries. Every point on those points are equilibrium. So, if you move away from those points, you will get only a single phase existence, because that single phase should be at a lowest energy level or equilibrium. Okay. So, that equilibrium concept gives us this phase diagram, which is pressure and temperature, and over that we have three phase coexistence. At only one particular point, three phase can exist under equilibrium, but all the other points on those lines, there should be two phase equilibrium. So, let me stop here. So, we will continue. Thank you.